Hello and welcome to this lecture on fatigue lifetime. What I'll cover in this segment of our lectures are two different methods. The first one is we'll talk about strain life method, and the second is going to be devoted to a preliminary understanding of linear elastic fracture mechanics. In the previous introduction to fatigue, we mentioned that we have three different methods that are used for fatigue lifetime assessment. The most common is the stress life method, which is called the SN method in many applications, and it is the simplest, and we discussed some aspects of that before. The second is what I will cover here, the strain life method, and it's generally important when we discuss low cycle fatigue, when the lifetime is generally below 1,000 cycles. For example, a takeoff and landing gear assembly that goes through these cycles and then fails after 1,000 cycles. So in these situations, we have to pay attention to ductility. And more recently, there are efforts to include linear elastic fracture mechanics as an additional tool for analysis of fatigue life. So let's first consider the strain life method and then move on to the linear elastic fracture mechanics area. So in this approach, we have the strain life method. We use detailed analysis of plasticity, and moreover, when we have plasticity, we have cyclic to include cyclic plastic deformation at localized regions. So that becomes very important. And it is, for example, if we have a cooling channel that looks like this, and we are subjecting the component to high heat flux, for example, here, and we get stress concentrations close to the corners, like, for example, this corner, this corner, this corner. Then if you look at cyclic plasticity, then you see that in this corner you're going to have a plastic deformation, and the plastic deformation can progress from cycle to cycles. Based on that, we get a strain, and the strain accumulates as a function of position x. And based on the strain, we have a limit. The material cannot be stretched beyond a certain limit. Then we want to find the lifetime. So the idea here is that this type of approach is very detailed and takes into account the cyclic nature of plastic deformation, and it takes knowledge of running computer programs using elastoplasticity and accumulation of the strain from cycle to cycle. I will just cover the basis for the step from having knowledge of the strain at a certain location to saying something about the lifetime that corresponds to this strain. So let's move on to that one, and we'll see here that in this strain life method, I will start by plotting a simple behavior for a fatigue test, and this simple behavior is going to be for the case of an applied strain. So if I have delta epsilon applied, so I applied to be fixed delta epsilon, then I will get the stress. So let's say that we have delta epsilon is applied and fixed. Then the question is, how can we plot the corresponding delta sigma as a function of time? In this case, we would expect that the stress is going to increase and then decrease in the cyclic fashion as we just apply a fixed amount of deformation. So let me just make it a little bit consistent here. So we have cycles like that for the stress, and the cycles for the stress can result in softening. So you get the stress can decrease until we get to a saturation stage. So in this case, I would see that I have an envelope, and this envelope here would dictate the stress cycles as a function of time, t. And we would call this behavior softening. Okay, so the delta sigma is applied as fixed. So if I plot underneath here delta sigma, I will get fixed amount up and down. So this is here the applied delta sigma. So this, while this is fixed, the stress will decrease from cycle to cycle. So this is kind of a common test that we use in practice, where we apply a deformation or a strain amplitude that is fixed in time, and then we can measure the force and hence the stress. As I mentioned, we can get softening or we can get hardening. So either one of these is possible. Now let's assume that we get this data and we want to represent not the stress versus time, but we want to represent the stress versus strain. How is this going to look like? So let's see here how this we expect that to look like. So in this case, I will have the behavior for the stress versus strain. If I plot it here, I will call this delta sigma versus delta epsilon. So this is delta sigma here versus delta epsilon. And if I look at the results, I'll see that initially it's going to be a straight line similar to a tensile test, and then we might get some plasticity. And then when we reverse the cycle, then we get stress reversal, and then we will continue in the next cycle. We get something like this, and the next cycle, and so on. So this is cyclic plasticity. And cyclic plasticity is a relationship between the stress and the strain when you have many cycles. So in practice, it will look like that. So in this case, I have a fixed applied delta sigma. So this is fixed. And the delta, so this delta epsilon is fixed, sorry. And the delta sigma is changing. So this is delta sigma initially. It was this amplitude. And if you follow the first cycle, it will go to point A. And then you have a reversal, and then it will continue to point to here, and then you go to point B, and so on. So you can see that the tips here are decreasing. In other words, delta sigma is decreasing with time as we had plotted them. In this case, as you can see, the delta sigma is decreasing as a function of time. So for this particular softening behavior, we have a limit cycle, basically, for the relationship between the stress and the strain, that we would have a hysteresis loop that repeats itself after several cycles, maybe 5 to 10 cycles, you reach that point. Based on that, we can develop a lifetime prediction criterion based on the decomposition of the strain. What we will see here is that we have a relationship between delta sigma and delta epsilon from cyclic behavior. Cyclics, this is very important, is not uniaxial stress strain. And given applying a delta epsilon, we'll get a delta sigma, and so on. So if we make a table of delta sigma versus delta epsilon, in other words, each one of this will be considered one experiment, in this case one experiment, and the one experiment will lead us to a saturation cycle, and the saturation cycle will eventually give us the relationship between the applied delta epsilon that is fixed and the saturation value of delta sigma that results. So this is the result, and this is the applied. So if we make many different applied values of delta epsilon, and we obtain many different values of delta sigma, we can tabulate these results in a table, and that table can give us a relationship between some value of delta epsilon, some corresponding value of delta sigma, and so on. So we'll get a relationship that looks like a stress strain diagram. So you will have delta sigma and delta epsilon, and the results now would have a linear part, and then it will be going like this until you get failure. So this is very similar to the stress strain diagram in uniaxial testing, but the difference here is that we have to make many experiments that involve, each one involves many cycles until we get to the saturation cyclic behavior of a saturated plasticity loop. And from that, we extract only two numbers corresponding to the tip of that cyclic loop, and that is the relationship between delta epsilon and delta sigma. So having done that, then we have a database now that we can call a relationship between stress and strain in fatigue, under fatigue conditions. So it is a little bit different from the uniaxial, as I mentioned before. And the concept for lifetime is based on the partition of deformation. So the deformation strain, delta epsilon, and we're going to have this to be divided by 2 because we have half in tension and half in compression. So we can write delta epsilon over 2 is composed of 2 parts. One is delta epsilon elastic over 2, and the other one is delta epsilon plastic over 2. As you can see here, in this region here, you have mainly elastic, and then as you go on to larger and larger strains, then the contribution of the plastic component becomes more significant. And the design is based on this partition of strain. So let's develop now how this will work for design applications. So let me add one more page here, and then we can consider cyclic plasticity in that case. So in this case, if we wanted to plot results of delta epsilon, either elastic or plastic, as functions of the number of cycles, n. But since the number of cycles could be small, then usually we plot it as a function of the number of reversals, 2n. This is number of reversals. So each reversal is half a cycle. So as a side note, let's assume that we have I'm going to do a little bit of math here to show you that the results can be represented easily on a log-log plot. Most of the fatigue data are represented on a log-log plot. So I'm going to do a little bit of math on the side before I get into this important relationship between delta epsilon and 2n. I will assume that I have a function, and then that the function is of the power law form. So let's take this function, for example. If we assume that I have a mathematical function that y is equal to x to the power b, for example, then if I take the log to the power 10 of y, in this case, so if I take log of y, I will have b log of x. And suppose that I have a constant in front of the x, then this will give me also log of k. Then this equation here, if I represent on a log-log plot, if I let log of y be equal to z, for example, and log of x be equal to, let's say I have maybe beta, for example, as a new parameter, then I can write this as z is equal to, and then I'm going to let log of k equals to a new constant. So z will be equal to a plus, and then I have b is the same, log of x is beta. In other words, I have an equation of a straight line between z and beta. So this is z and this is beta. And the slope of the equation is this constant b, which is, if I write it here, bb to 1, that's the slope of the straight line. In other words, what you gather from here is what we've learned before, is that if you represent data on a log-log plot and the representation is of the power form, then the slope of the straight line that results is the value of the power that you raise the variable to. And that's basically the basis for the following equation that we will develop here. So the idea now is that we can see that the fatigue data can be represented in as the accumulated strain amplitude, delta epsilon over 2, versus the number of reversals to failure. And the total relationship between the two is this line here, the red line. So this is total. And we're going to decompose this relationship into two parts, as we mentioned. Delta epsilon over 2 is equal to delta epsilon elastic over 2 plus delta epsilon plastic over 2. And each one of those, we will represent it by a power law. So if I write delta epsilon elastic over 2 as a new constant, I'm going to call it sigma f prime over e times the number of reversals to power b. And I write delta epsilon plastic as a new constant, epsilon f prime times 2n to the power c. Then each one of those separately, for example, this one, when you present it on a log-log plot, then you get a straight line for the plastic strain. So you'll get this straight line here, as you can see here, it will be for the plastic strain only. And the slope of that straight line is, for the plastic strain, is c. And similarly, for the elastic strain, you get a straight line with the slope of b. Notice that these are, if you present each one separately, you'll get a straight line, and then when you sum them over the log plot, you get the total strain. So this method allows us to write the total strain into this decomposition with a bunch of parameters. So the parameters here is that we have a fatigue ductility exponent, C, So that needs to be measured. And for the plastic strain line, and the fatigue strength exponent B, that needs to be measured for the elastic strain line. And moreover, we have two additional parameters. One of them is the sigma f prime, and the other one is epsilon f prime. So we have fatigue ductility coefficient epsilon f prime and the fatigue strength coefficient sigma f prime. So these are four parameters for each material that need to be known. So in this kind of decomposition, we have to find data from extensive testing, and the data will give us four numbers, the B and the C, which are the exponents, and that come from the slopes of the straight lines if we fit the data, and then the epsilon f prime and the sigma f prime, and that also come from the intersections of the straight lines with the vertical axis. So that it is possible to get these four components, and therefore we can actually allow the representation of fatigue life based on this idea. So if you look at that, you'll see that the final result is that when we apply the total strain amplitude, we get a representation that is decomposed, as you can see here in equation 6.3. And moreover, when we have this data, we can determine if we have reached. So we have to do the analysis to find this part of the strain from, let's say, finite element or from estimation, and this part of the strain from also finite element or estimation. And since we have the parameters A and B and epsilon f prime and sigma f prime determined, then we could use this equation to tell us if we've reached the maximum allowable strain limit before fatigue takes place. This type of analysis is very well known as the Manson-Coffin relationship. A Manson-Coffin relationship is important because it is the only or one of the most reliable relationships that we can use to study fatigue based on strain life criteria, assuming that we have the data for these four parameters representing fatigue life. So that's basically what we will have in this approach. And as I mentioned, it takes some more work in terms of analysis to get to these numbers. So generally, we would apply it when we reach a higher level of design using elastoplasticity in a cyclic fashion. Now, the last topic that I wanted to cover today is linear elastic fracture mechanics. We have mentioned that before when it comes to fracture processes, that we discussed the idea that we have to compute the stress intensity factor ahead of a crack tip, and then we have to compute the shape factor from given tables or graphs that are provided in design books. And between these two, we can determine the local stress intensity factor of a crack in a given configuration, compare that to the fracture toughness, and if the stress intensity factor exceeds the fracture toughness, we determine that we have complete fracture by fast fracture, basically. Now I'm going to take this and look at what happens under fatigue. Under fatigue conditions, you might imagine that the crack is going to be up and down and is going to grow very, very slowly. And that's basically the case that it's been found that the growth increment for the crack size is related to the stress intensity factor raised to some power. This relationship is very well known and is known as the Paris equation because the developer of the relationship, his name is Paris. So let's look at the Paris relationship that helps us to discuss crack growth. So in this relationship, we know already that the stress intensity factor is made up of a shape factor that we can obtain from the tables or the graphs provided in manuals. Sigma is the remote stress. In other words, it is not the local stress close to the crack, but it is the applied nominal stress. And A is the half size of the crack. So if I have a crack like this, and the size is 2A usually, if it is an embedded crack, if an edge crack, the size is just A, because it's half if it is an edge crack. Now, if I'm cycling, what happens is that the stress will go up and down in time. So since K is, as you can see, beta times sigma times square root of A, then as the crack opens and closes, then the stress is going to be changing as a function of time, and the shape factor is going to be changing as a function of time, because the crack is going to propagate and its size is going to change and in relationship to the size of the structure. And also the crack size itself will change in this equation. Therefore, the value of K will keep changing as a function of time to the worse. In other words, it will just keep increasing until eventually its value will reach a point where the fracture will occur dramatically by brittle fracture or by limited ductility. And that's when we reach either a limit on fracture toughness, or we reach a limit on plastic deformation and failure by yielding. So that's kind of the idea. And in here, what we to characterize that, we will define the stress intensity range. The stress range is delta sigma, and the stress intensity range per cycle as the same beta, but now the difference between maximum and minimum stress times the square root of A. So it is basically delta K 1, this is 1, not I. Delta K1 is beta times delta sigma square root of A, and delta sigma is what you have when you do the test, the fatigue test. So if you have here sigma as a function of time, then you have sigma max is right here, and sigma min is right there. Then the difference between sigma max and sigma min is given. Or if you have a test that gives you fatigue data that go up and down with a mean value in between, so this will be your sigma max, and this will be your sigma min, and you take the difference to get the delta sigma that is required. So the Paris law is kind of an empirical law that describes the growth rate of the crack per unit cycle, dA by dN, versus the delta K that we describe. So delta K is beta delta sigma square root of pi A. So if you plot that relationship, you see that all the data, fatigue data, will be scattered, and you will have on a log-log plot 3 regions of behavior. The first one is crack initiation, region 1, and then you get for very low values of delta K, and then we would get into region 2, which is the majority here, which is presented by a straight line, and that is a region of stable crack propagation. And then we get region 3, which is when we get closer to K sub C, which is the fracture toughness. As delta K gets closer to the fracture toughness, then the crack will propagate in an unstable fashion, and you get immediate fracture, not delayed fracture. So if you look at region 1, it is represented by a threshold value, delta K threshold, below which you cannot detect crack growth, and above which you have some level of crack growth. And if you get an applied value of delta K, for example, here, then you can actually find a value for dA by dN, which is the rate of growth of a crack with respect to one cycle. If we want to find the lifetime, then we need to integrate the dA by dN as a function of the number of cycles. So to determine the lifetime using linear elastic fraction mechanics, I need to represent dA by dN as a function of delta K. And delta K, as I mentioned, has three things in it: beta, delta sigma, and also square root of pi a. And then I integrate this function with respect to n to determine how large the crack is going to grow. And when the crack goes to a certain value, a critical value, then I will be able to say that the structure has reached its limit, and then we get failure. So this is kind of the procedure that we will pursue. And if you think about it, in reality, this is going to require numerical evaluation. Why? Because for dA by dN is not a fixed number. Beta keeps changing because the shape of the crack and its location in the structure will change. Delta sigma can be changing because the applied stress is applied, but then at some point it could change. Therefore, the crack can grow in a different fashion if we change applied stress. And then finally, the size of the crack will change, and therefore we have to take that into account. So the general story is that we do numerical integration. However, for quick calculations, we could make some simplifications and solve problems analytically, and that's what I'm going to do next. So in this case, I have to look at analytical solution to these crack problems. Before I go there, I wanted to make some comments on the numerical values for crack growth in region 2. This is described by the famous Paris equation, and the Paris equation has two parameters, C and M, because it is empirical. So we need to have data, empirical constants. And for design purposes, if we have ferritic pearlitic steels, the constant C has a units of MPa square root of m to the power m, where m, let's say, is 3 here, and its value is 6.89 times 10 to the minus 12 in megapascal square root of meter to the power m. Similarly, for martensitic steels, you get higher growth rate per cycle, and for austenitic, you get lower, and these are the corresponding exponents for each case. In other words, each material, we could use the two constants that Paris equation will give us to describe crack growth. And in order for us to determine the lifetime, we integrate, we have dA by dN is equal to C times beta times delta sigma times the square root of pi a, all of this to the power m, because we have Paris law. This is basically delta k right here. Then I can actually take the dN to the right hand side, and I can take everything else to the left hand side, and this is what I have in equation 6.6. So the integration of dN from 0 to nf is the final, give us the final estimated number of cycles to produce failure. And I have the Paris constant C and the second Paris constant M, and then I can do the integration if I assume the beta is constant, I can pull it out. Delta sigma is constant, I can pull it out. And I can leave the square root of pi a inside the integral. That's no problem. Notice that I must know an initial crack size and a final crack size. So let's discuss those parameters in a second. The initial crack size is always determined by inspection. So you do ultrasonic inspection as an example, and then it has a minimum detection limit. Suppose that this is 1/1000th of an inch, reasonable number. It depends on the method of inspection. There are other inspection methods that can go down to the micron level, but for most parts, we would be content with 1/1000th of an inch. And then you grow that crack up to a maximum value. The maximum value, we have to decide what is the maximum value. And we will decide based on two criteria, either that we reach a plastic yield point because the remaining section cannot carry the load, or we've reached an instability that causes immediate fracture because the stress intensity factor is larger than the fracture toughness. So either one of those, and that we will take examples to illustrate this idea. So before we go to these numerical examples, I wanted to comment on an algorithm, and the algorithm is something that you can program in MATLAB. That the previous equation, you can write it as delta A sub j, where we have an interval, a time interval j. So you can determine how many cycles in that time interval. Could be 1 cycle, could be 10. So this is delta nj is 1 or 10 or 15, whatever you want to decide. For that number of cycles, we would consider both c and delta k to be constant. So from within this small number of cycles, we can consider those two parameters to be constant. So if we do an integration, then the crack size in step number j plus 1, interval j plus 1 is equal to the crack size in the previous interval plus the increment that has occurred, assuming that these two are constants. And that's very simple integration. You can just add the results and then you increment the number of cycles. So we have now a new number of cycles. And then you keep looping. So we have to have a for loop until we reach the final limit that is based on a final, and a final we can obtain from plasticity, meaning yield, or from the K1C, which is the fracture toughness. So these are the considerations that we have in here for numerical integration. So now I'm going to just go over two examples, and the two examples we will show that I gotta bring this back here. The two examples I'll show that I have, let me just get, all right. So in these examples, I'll show how to do these types of calculations for crack growth in a very simplified geometry under very simplified conditions, because we need to do some analytical solution. So in this example, I have a beam, and the beam is under bending moments and is subjected to a repeated moment that goes from 0 to a maximum 1200 pound-foot-inch. And the bar is an IC 4430 steel, and it has the ultimate strength of 185 kpsi. Yield is 170, K1C 73. So what I will do is I'm going to use this value to judge on the final crack size, or this value. So either one that gives me the smallest. And we got the two constants, the C and the M for the material. And we also have from the inspection is 4/1000th of an inch have been discovered. So we have a nick here and it's going to propagate. So the first step is that we want to calculate delta sigma. Delta sigma, first we have to find the z modulus, which is I over c, and delta m over z will give me the delta sigma. This is the oscillation in the stress, and therefore the stress goes from 0 up to 115.2 ksi, and that is the delta sigma. And with each cycle the crack will grow, so I need to find beta. So initially I will assume that beta is equal to 1, and then I can modify my assumption a little bit later. And I'll also try to find the final value of the length of the crack using K1 is equal to K1C. So I need to find K1 is sigma square root of pi a. That's the K1. And then when I equate it to K1C, which is given to me, then I can solve for the final length of the crack to be 0.1278. And therefore the crack is going to propagate from 0.004 of an inch all the way up to the 0.1278 inches, and I need to find in how many cycles. Before I go too far, I wanted to make sure that I have the right ballpark figure for beta, and beta is the shape factor, so I go to figure 527 in Shigley that gives beta as a function of the A over H ratio. A is the crack length and H is the depth of the beam. So if I look at for the final, is A over H is 0.25. For the initial, A over H initial is very, very small, close to 0. So if I look at this graph, then the beta is going to vary over the lifetime on that curve here. And as you can see that the beta variation is not very significant, so I can assume some kind of a constant value just to get myself going on the numerical integration. And that's what we did here. So we assume that beta is nearly constant at 1.07. It's kind of an assumption to make the integration easier. Otherwise, I'll have to find the equation of this curve and include it into the numerical integration. And I don't want to do that here. So I wanted to have reevaluate A final with this beta, and then integrate from A initial to A final. I know A initial 4,000, so A final is 0.112, and I know the delta sigma, and the beta now is fixed, and therefore the integration has only dA over square root of pi a to the power 3, which is easy to do, and that gives me the number of cycles to be 64.7 times 10 to the power 3. And I think this example illustrates how we would do the calculations using linear elastic fracture mechanics. In other examples that we will have on the homework assignments, the maximum value for the crack size could be determined from yield. So you have to always check on whether yield is approached first or fracture as a result of the stress intensity factor exceeding the fracture toughness. Otherwise, the procedure is easy to apply, and we'll use it in several occasions during office hours and during the preparation for the homework assignments.